Great, welcome back. So today we are going to be looking at predicting redox reactions. So just being able to tell if a redox reaction will actually occur or not. So first little things first, we know redox reaction is a transfer of electrons from one substance to another. So another way we can actually think about redox reactions is that they can be explained as a competition for electrons between the two reacting entities. So of course, one thing is able to pull the electrons away from another substance, and that creates that redox reaction. Now, just for the first little bit right here, what we're going to be going is looking at oxidizing and reducing agents. So of course we have this little asterisk here, so just be careful with the names and the processes that they undergo. So it'll make a little more sense once we get going. So important, in all redox reactions, electrons are transferred from a reducing agent which we're going to label RA for short, and so electrons leave the reducing agent and go to the oxidizing agent. Which we're going to label OA, as this little graph says right here, right? So electrons leave the reducing agent, go to our oxidizing agent. So how they get their names, or why they got their name, was a reducing agent, or RA, promotes reduction. So it does this by donating or losing electrons. So in other words, it's oxidized. So let's repeat that again. Reducing agents promotes reduction. So that's why they get their name. They force something else to be reduced, and they do that by losing their electrons. So it is indeed oxidized. So generalizations for reducing agents is generally stuff with low electronegativity, so metal elements, or nonmetal ions. And nonmetal ions already have that negative charge, so of course they're able to lose that negative charge, and that's why they make for good, generally good reducing agents. Now, oppositely, our oxidizing agents promotes oxidation by removing or gaining electrons from another substance, so in effect is reduced. So generalizations for oxidizing agents, we have high electronegativity stuff, so nonmetal elements, or metal ions generally work as well. So just a little note here, oxidation and reduction refer to the reactions, whereas oxidizing agent and reducing agents are the chemical species that are causing the reactions. So that's why we have to be careful with the process. So for example, we have A, B, C, and D. So we're going to show oxidation and reduction by using arrows and label OAs and RAs. So you can kind of pull these apart like you did when you did balancing complex half reactions and stuff like that. Or what we can do is just kind of look at the charge and figure out what is happening. Right. So for example, with our silver, we're starting with silver plus, and over here it's silver solid. So we can tell that that positive charge had to go somewhere, so it is being reduced. In this half reaction, and our copper is starting with no charge and now going to a 2 plus charge, so copper is being oxidized. So that makes my copper solid my reducing agent, and my silver plus is my oxidizing agent. So same thing in example B, you figure out what is happening. So we got bromine as a liquid over here, now it's an ion. We can tell that bromine, in order to go from a 0 charge to a negative charge over here, it needed to gain electrons, so it is reduced. So that means the I minus going to I2 is oxidized, which means now my I minus is my reducing agent, and my bromine is the oxidizing agent. Now, before I fill in part C, it would be nice to kind of pause the video and see if you can get this one on your own, all right? And what you should get, nickel 2 plus is the oxidizing agent, and calcium solid is the reducing agent. So on the next page as well, we have more practice with writing out half reactions and kind of saying where everything goes. So what we have right here are balanced half reactions, balanced full reactions, and your goal is to write out the oxidation half reaction, reduction half reaction, and then identify the oxidizing agent and the reducing agent. So you can kind of do it same thing as we did on the previous page there, is that you can just generally to figure out which one is which, right? You can have a look at what's happening to the charge. So you can tell Br2 is going to be R minus. So as an element, it has a 0 charge. Over here, it has a negative charge, so it is reduced. Whereas the tin 2 plus going to tin 4 plus is oxidized. So we can write in our oxidation reduction half reaction. Balanced by mass, we got 1 and 1, so that's fine. Now we get balanced charge, 2 plus, 4 plus, so we need 2 electrons. And my reduction half reaction looks something like this, balanced by mass, which is balanced, now balanced by charge. And we have our reduction half reaction. So now we just fill in, so my reduction half reaction, my oxidizing agent is the thing that's being reduced. So it is bromine, and my reducing agent is my tin 2 plus. Now just remember, oxidizing agent and reducing agent are always going to have to be the reactants as well. Alright, so that's kind of how you do that. So please pause the video right now and try the next 3 on your own, and the answers are going to be up in 3 seconds. And here are the answers, so just make sure that yours matches up. So we have all the oxidation and reduction half reactions there, and then of course our oxidizing agents and reducing agents are always the reactants, and of course please pay attention to their charge and state of matter and everything like that. So from here, we're going to look at kind of where this kind of takes us, this whole idea of oxidizing agents and reducing agents. And this is where we get into our extended redox table. So this was developed from many experiments, so empirical evidence that has been collected and analyzed. And what this table is used to compare the strength of oxidizing agents and reducing agents to predict if a reaction will be spontaneous or not. So this is found Appendix 1 of your textbooks on page 7 of your Chemistry 30 data booklet. So it looks like this. So it should read table of selected standard potentials, and we have reduction half reactions all here, and this whole electric potential thing, we'll kind of get into this when we get into electrochemical cells, but we have a lot of different reactions here. So this table shows reduction half reactions. Now you will notice that there's double arrows. So this means that the reaction can be read in both directions. So even though these are all reduction half reactions, we have that double arrow here, meaning that we can read it from right to left, or we can read it from left to right, or left to right to right to left, sorry. So, for example, the oxidation half reactions are in the opposite directions of our reduction half reaction, so if we read it from right to left. So for example, if we wanted to show the reduction half reaction and the oxidation of dichromate ions reacting under acidic conditions. So we can just pull from our data booklet our dichromate ions. It's going to take a while to get used to this one right here, is the first one right here. So we have Cr2O7 minus, plus 14H plus 6 electrons, then plus produces, 2 chromium ions and 7 H2O. So we can just take this and transfer it into our part right here. So it'll look something like that. So that is the reduction half reaction of the dichromate ions. So that is reading the table from left to right. Now with that double arrow, of course, we can also look at it in the reverse direction, and that will be an oxidation half reaction. So that's kind of taking this whole equation right here and just reading it in reverse. So of course, if we do that, it'll start off with 2Cr3 plus Aq plus 7 H2O liquid, producing Cr2O7 minus, plus 14 hydrogen ions, and of course 6 electrons. So that means technically, even though that table does say it's just reduction half reactions, it's technically both. We have reduction and oxidation half reactions. Now, because these are all reduction half reactions, so on the left side we have all of our oxidizing agents. Now, how these are listed as well, they are listed from strongest to weakest. So that means that right up at the top right here, as we go up, right, they get stronger oxidizing agents as we go up. So our strongest oxidizing agent, we use abbreviation SOA, is at the top right. And of course, the one at the top right is fluorine gas, which makes sense. It is the most electronegative element that we have. Now, our reducing agents, because if we read them in reverse, now over here, right, so these are all oxidation half reactions if we read them in reverse. So on this side right here, our right-hand side, these are all of our reducing agents. And they are listed from weakest to strongest. So as we go down with these here, as we go down, that means they get stronger as we go down. Oops, sorry, SRA, not OA. As we go down. Oops, sorry. So that means our strongest reducing agent is at the bottom right. I'm sorry, it's not top right, it's top left. I get my left and rights mixed up all the time. Sorry about that. So just go back and fix that. So top left. Oops. That kind of shot down there for a second. Having some technical difficulties here. All right. And the strongest reducing agent, of course, if we go back and try to figure out what is at the bottom here, we see bottom right, we have lithium solid. So we are going to use this table right now to kind of help predict reactions. So spontaneous reactions, these are reactions that occur without input of energy. So no heat, no light, no electricity or anything like that. So normally for evidence of spontaneous reactions, you get bubbles, see a color change, temperature change, precipitate forming, stuff that you see before, like if, something visible is actually happening. Then, of course, a non-spontaneous reaction will not occur unless input energy is supplied. So you're going to see words like this. So no evidence of reaction, non-spontaneous, no reaction, non-spot. Just little things like that. So in order to predict if something was a spontaneous reaction or not, we're going to use the spontaneity rule. And this was developed with our table. So the spontaneity rule states that a spontaneous reaction occurs if the oxidizing agent, the OA, is above the reducing agent, the RA, in our table of redox half reactions. So as long as oxidizing agent is above reducing agent, we have a spontaneous reaction. If it's the other way around, if the oxidizing agent is below the reducing agent on our table, it's non-spontaneous. So we have a bunch of different examples right here. So the big thing is just finding where they are on our table, and then of course figuring out if it's going to be spontaneous or non-spontaneous. So our first example, we have chromium 3 plus with silver solid. So you're going to have to go to your data booklet and try to find chromium 3 plus and of course silver solid. Right, so it's going to take a while to get used to it. You'll see the chromium 3 plus over on this side right here. So this is my oxidizing agent because it's on the left hand side. Now to find your silver, now just be careful because this is silver with iodine. We don't have that, we just have silver by itself, Ag, and you'll notice it's up here on the reducing agent side. Now we will notice that in this right here, my reducing agent is above my oxidizing agent, so therefore this is a non-spontaneous reaction. All right, and that's how we use our table to figure out if it would be a non-spontaneous or a spontaneous reaction. All right, so 2, 3, 4, 5, and 6 2, 3, 4, 5, 6, and 7 are all here. Now some of the ones here, just be careful when you start getting down here. So silver and Br minus, like this one here, MnO O4 and H plus, that means that two of these together is either going to make it an oxidizing agent or a reducing agent, right? And of course, just kind of spoiler ahead for that silver and that bromine one, in your data booklet, you'll notice that, well, silver was right here, but if you go down, you'll see silver solid and bromine. So this combination together makes it a reducing agent. All right, so you'll need to kind of figure out where that one is. But please kind of pause the video and see if you can go through and get the answers. And I'll put the answers up now in 3 seconds. And here are the answers. So of course we have 2 is spontaneous, 3 is spontaneous, 4 and 5 are both non-spontaneous, and 6 and 7 are spontaneous as well. So all the spontaneous reactions, the oxidizing agents, were above the reducing agents on our chart, and the non-spontaneous ones, just like our first example there, where our reducing agent was above the oxidizing agent on our chart. And of course, this kind of ties into a little diploma example we have right here. So which of the following metals will act spontaneously as a reducing agent with silver iodide, but not with silver sulfide? All right, so of course, this right here, we know that silver iodide is a Gi, right? So basically what we have right here is the silver ion and this iodide ion. Of course, silver sulfide is going to be Ag2S. All right, so in order to answer this one here, you are using our data booklet. So you find both of those right here, right? Our silver iodide is right here, AgI, and silver sulfide is, I'm trying to find it here now, silver sulfide I believe is down here. So of course this one's asking about which one of these here is going to act spontaneously as a reducing agent and not with silver sulfide. So basically we're looking for the combination of the two things that have to be right here, where I believe nickel and cadmium, or sorry, nickel and chromium. Right, so this one here, spontaneous, non-spontaneous here. So our answer is C. Now, kind of what page 7 is in our data booklet, and it was kind of brought up there as well, like these are just all based on observable properties, and of course they did reactions to figure out which ones would be spontaneous and non-spontaneous. So one of the things that we're actually going to do is generate our own redox table, so similar to page 7, except with chemicals that generally don't show up there or even unknown stuff. All right, so what you have to remember though is when we are kind of building our tables, remember reducing agents is always placed at the bottom right, or the strongest ones, and our oxidizing agents are always going to be on the top left. So let's look at how we can actually build one of these tables together. So one thing that you could be given is a bunch of reactions like this. You have to figure out which one's your oxidizing agent, which one's your reducing agents, and then build our own table based on what we have right here is just a check mark if we have a spontaneous reaction and a non-spontaneous reaction. So our first step is to figure out, okay, which one's going to be oxidizing agents, which one's going to be reducing agents. So you can always remember metal elements always generally lose electrons, right? So if they're losing electrons, they're oxidized, which makes these my reducing agents, and up on top here is my oxidizing agents. Now, when we're looking for the strongest oxidizing agents, obviously the ones that react the most should be the strongest. And we can tell right here, silver reacts with copper, zinc, and lead. So my strongest oxidizing agent is going to be silver, right? So if I'm writing out reductions half reactions in correct order, my first one, my strongest oxidizing agent should be my silver. Going to silver solid, right? Because it reacts 3 times. Now the one that reacts second most is my Cu2+, so it is the second strongest. And then we go to our third strongest, so my lead 2+. And then finally, the one that didn't react at all, my zinc 2 plus, that obviously must be my weakest oxidizing agent. Alright, so by generating a table, it looks like this. This looks like a little mini version of what we have on page 7 based on, I know, my strongest oxidizing agent based on the reaction, so the observable properties, and then of course second strongest, third, and then of course the weakest. Alright? And then of course from here we can now list out strongest oxidizing agent in order from as I said here, so put the oxidizing agents in order from strongest to weakest. So you got Ag plus, Cu2 plus, Pb2 plus, and zinc 2 plus. All right, strongest, weakest. And of course we can even put our reducing agents in order from strongest to weakest as well, because we know our strongest reducing agents down at the bottom here, so that's our zinc solid, and they get weaker as we go up as well. So we can then go zinc solid, lead solid, copper solid, silver solid. So that's kind of all the information we can get from here, and of course we do need to be able to have an entire chart like that with all of our reactions. Now sometimes we're not going to be given a nice chart like that, we're just going to be given a select few. So in order to generate our redox tables, we are going to have to create a T-chart. Now this is optional, but it's just a way to organize your data. All right, so a T-chart gets its name because, well, it looks like a T. All right, so where we're going to have our oxidizing agents and our reducing agents on one side. So we're still going to try to keep it like this, and the reason why is that we're going to use our data, but we're going to take the order that they're coming in right here and then transfer it down here later to basically create our own little table. Now we are going to be using the spontaneity rule to figure out if something is spontaneous or not, and then we're going to put them generally where they would show up here. So for example, let's look at the first one where we have copper plus silver and we have a reaction. Now, by looking at this, I can tell copper is getting oxidized, so that means Cu solid is my reducing agent, and Ag plus makes this my oxidizing agent. Now, because this is a spontaneous reaction, that must mean my oxidizing agent is above my reducing agent on my table. So I'm not going to start right up at the top here because I will need to add things in later, but I know my silver solid is above my reducing agent because we have a spontaneous reaction. Now from here as well we can put in their counterparts, so silver solid, copper, and copper 2 plus. Now my next one we have right here is zinc 2 plus and silver solid, so I know silver solid is my reducing agent, which makes zinc my oxidizing agent, and I already have it over here now, no reactions. So that means my reducing agent is above my oxidizing agent. So that means zinc is going to be somewhere down here. Now the thing is, I don't know what zinc is like when it's compared to copper, so that's why I'm looking at my second reaction, and I find that when zinc solid, which is a reducing agent, is mixed with my oxidizing agent of Cu2 plus, we have a reaction, meaning that my oxidizing agent is above my reducing agent. So therefore it's going to look like this because we have that spontaneous reaction here between Cu2 plus and zinc solid, and a non-spontaneous reaction between zinc 2 plus and silver solid. And then finally the last one, we have mercury liquid with zinc plus, or sorry, silver plus. So silver plus we already know is oxidizing agent. This is a reducing agent. We have no reaction, meaning my reducing agent is above my oxidizing agent, which is right here. And then mercury, the other one, should be 2 plus. So now that we actually have the general position on where everything is, now we can actually create our table of half reactions, right? Where you know our strongest oxidizing agent is going to be at the top left, and that is our mercury 2+. I chose 2+ because that was the most common charge for mercury. So its reduction half reaction look like that. Use a double arrow. We go Hg liquid. Next, silver plus an electron, produces Ag solid. Next, copper 2+, and finally, the last one. And we know this is going to be my strongest reducing agent down at the bottom. So that's kind of how we use a T-chart. And all it is just an organizational tool to get the general positions of these here, so then we can then create a table of reduction half reactions. And then, of course, just finishing out this question here, it says put the reducing agents in order from strongest to weakest. So that means the reducing agents, we have zinc solid, then copper solid, then silver solid, then mercury liquid. That's how we do those. So there's a bunch more here, so it would be nice if you actually pause this video right now and try the other ones. If not, I'm just going to go through them step by step there, just with their answers on what the redox table will look like. All right, so see if you can get this one on your own based on these unknown elements and the observation if there's a reaction or no reaction. So I'll put the answer up in 3 seconds. Should get something that looks similar to this. So the T-chart's just off on the side here. Now, the ones I put in green, these were the spontaneous reactions that were here. So between Z3+ and Y plus and W. And then, of course, the non-spontaneous ones I just kind of put in red. So I just drew lines at the reactions that were just tested with here. And this is how we can kind of fill out where everything is. So in our table of reduction half reactions will look something similar to that. And then, of course, if we're putting the oxidizing agents in order from strongest to weakest, now it's oxidizing agents. So we have Z3+, Y+, A3+, and W2+. And I believe this is the last one before a diploma question shows up. So same thing, it's generate a redox table just for the following reactions. Now there's only 3 here, but there's more than enough information. Now just be careful with the charges, and notice that these are unknown, but these are diatomic, so you're kind of making the connection there as well. It's like the only other diatomics are the non-elements, and these here are negatively charged. So we know our negatively charged ions are generally good reducing agents, which makes these here oxidizing agents, right? Because if X is going to, or we got Z minus, it's obviously going to be losing its electrons. And when you're done, your answer should be in this order. So if you do want to pause the video and give it a try, please do. But the order we should get is W2 plus 2 electrons versus 2 W minus. Then the next one is going to be, oh, not Zn, just Z2. And our next one is Y. And the last one, the weakest oxidizing agent, is X2. And of course, putting our reducing agents in order from strongest to weakest, we got X minus, Y minus, Z minus, and W minus. Very cool. And last but not least, the diploma question at the end, where we have our evidence and we're trying to figure out our oxidizing agents listed from strongest to weakest. Of course, we will need to use a T-chart for this right here as well. Right, where if we have a spontaneous reaction, we know that we have a 2 plus charge, and over here it is solid, so it is being reduced, making this my oxidizing agent. So we have COO2 plus must be above my ND solid. Next we have no evidence. So ND solid we know is a reducing agent because it's over here, so no evidence of reaction. That means that my Y3 plus is below it. And then we know that's going to be Y solid. ND2 plus. I'm just filling in these as we fill them in as well because CO2 plus is going to turn into CO solid, right? ND2 plus. And then finally, last but not least, the last one we got Y solid, which is right here, my reducing agent. No evidence of reactions. That means my SM2 plus needs to be down here, which means we know oxidizing agent strongest, so we got CO2 plus, followed by ND2 plus, followed by Y3 plus, followed by SM2 plus. So we get that. And of course, using our information up here, which equation represents a non-spontaneous reaction. So what we're doing is using the table that we have generated and looking at their positions between oxidizing agent and reducing agent to get that. And then of course, the only combination here that results in a non-spontaneous reaction should be C. Because if we look at our chart, if we got this one done right, if we take my oxidizing agent and mix with my reducing agent, so my ND2 plus and my CO solid, that gives me a non-spontaneous reaction because my reducing agent is above my oxidizing agent. So that is it for these here. Of course, inside your workbooks, there's going to be a lot more practice, so please practice with these here. I know the T-charts can be a little challenging to work with it, so make sure, try not to do it in pen, make sure to do it in pencil. And I'll see you guys tomorrow for the 5-step method.